Hello, this is Mr. Craig, and I want to make this video to explain this question that I have seen on the AP exam a few times, and it's pretty important because when I introduced this question to my students, they were a little perplexed by what the question was actually asking. So it's a pretty good question, and it was a past AP exam question. If you look at the homework tonight, I have reworded this question again. I just want you to get familiar and acclimated with the types of questions that could be asked. Now again, I don't have access to all the questions and the different ways in which they want to present the question, so I'm trying to get you guys to become familiar with the process, not necessarily the wording. Alright, with that, let's go ahead and get started. Question 1A says, several different electrochemical cells can be constructed using the material shown below. Write the balanced net ionic equation for the reaction that occurs in the cell that would have the greatest positive value for the cell. Now the question is asking for the net ionic equation. Okay, we have to keep that in mind. We have to know what the question is asking and answer the question accordingly. Here's what we're given. We're given some materials here, and we're given some chromium nitrate, we're given some magnesium nitrate, we're given some silver nitrate. We're also given some metal strips, some silver metal, some chromium metal, and some magnesium metal. And then we're also given a glass U-tube and a solution that'll fill the salt bridge. In other words, this glass U-tube will actually be our connection between the two chambers in which we choose to do this experiment. And of course, the wire to connect the two electrodes, the anode and the cathode. Alright, so here's what we have. Our task in front of us is to find out which combination of these three will give us the most positive voltage. And we want to have the most positive voltage. Not necessarily just positive, the most positive. Alright, so what we need to do is, we've got chromium, and the chromium ion here actually has a +3 because we had 3 nitrates. Obviously magnesium's +2 and the silver's a +1. So the chromium really is the only one that we should look at the non-metal closely for to understand what the charge is. So realizing that, let's go ahead and look at our standard reduction potential sheet. Or wait a minute, let me do this first. Let's go ahead and write the half reactions, the reduction reaction. So we're going to have chromium +3 when it's oxidized. When it's reduced, will absorb 3 electrons to form chromium ions. Get rid of that, sorry. Chromium ions. And then we'll also have a possibility of magnesium ions absorbing 2 electrons. And again, these are what are on our standard reduction potential sheet. And our last possibility is silver +1 absorbing or accepting an electron to form silver metal. Now, what we want to do with these 3 reactions, and honestly, you wouldn't want to write these 3 half reactions down. These are what you're looking for on the standard reduction potential sheet. So let's find the chromium +3 going to solid chromium. So looking at our standard reduction potential sheet, finding chromium +3 going to a solid. Now here's chromium +3 going to +2. That's not what we want. We want an ion going to a solid. That's what's happening when the system's being reduced, or vice versa. If we're going from a solid to an ion, we don't want to go through multiple steps. So actually our charge is right here. It's the chromium +3 absorbing 3 electrons, forming chromium solid, and that has a voltage of negative 0.74. So we'll go ahead and write that down real quick. Okay, and this is just information. We're not writing anything down yet. We're not even beginning to answer question part A here. Magnesium, so go back to the standard reduction potential sheet. Find magnesium, and here it is. Magnesium +2, 2 electrons, forming solid magnesium. Has a voltage of negative 2.37. So we'll write that value down. And then the last one, the silver, we have to go a little higher on the chart, near the top here. And silver with a +1 charge, absorbing or accepting an electron and forming silver solids, has a positive 0.8 voltage. Okay, so here's our data. And again, we were just looking at the standard reduction potential sheet and making notes. Now, I don't want to fill up my whole space here with these three equations, because that's not what the question's asking. But here's my question to you. We have three solutions: chromium ions, magnesium ions, and silver ions going to the solids, and that's the path we want to take. I want to know which of these three will we not use to make this galvanic cell. Okay? In other words, we want to have the most positive voltage that's available here. Okay? So we're only going to use two of the substances and two of the metals. We can't use all three of them. Okay? We have to have a reaction that's reduced, and we have to have a reaction that's oxidized. So here's my strategy. To figure out which one we're going to use for our reducing agent, or I'm sorry, for the reaction that'll be reduced, we want to find the most positive. Again, to find the reaction that we're going to keep as a reduction reaction, we want to use the most positive. So this one of the three, the silver ions, is our most positive. So this reaction we're going to keep as a reduction. All right? Now it's between the chromium plus 3 and the magnesium plus 2. In order to determine which of these two we're going to keep, we're going to look and find the most negative of the two. Because what we're going to do, since we've already established who our reduction reaction is, or the thing that's going to be reduced. Now we got to find out what's going to be oxidized, what metal will be oxidized. So I want to find the most negative. And the most negative, we're going to flip the equation, which means it will change the sign. So the thing that we will not use is our chromium. So magnesium is going to be oxidized, while the silver plus 1 is going to be reduced. Okay? So that's what we want to use. All right, now that we know which things we're going to use, now we can answer the question. So let's go ahead and do that. So we need to write the equation out. And again, it doesn't matter which one you start with. So silver plus 1, and we're going to write our reduction reaction first. You can write the oxidation first. It doesn't matter. And that'll form silver ions, and that has a voltage of 0.80 volts. And you don't necessarily need to write the voltage down for this. Actually, let me scoot that over. Okay. And then, because I like keeping my arrows next to each other here. And then we'll have magnesium metal that's oxidized, and that'll form magnesium ions and release 2 electrons. Okay, and that had a positive 2.37 voltage, and the silver had a positive 0.80 voltage. And again, those two values came from my standard reduction potential sheet. Okay, we are not solving for the voltage in this question. The question wants us to find the net ionic equation. All right, so make sure that you're answering the question, not answering questions that are going to be asked later on. All right, so finding the net ionic equation, we first of all have to balance the number of electrons after we figured out who's going to be reduced and who's going to be oxidized. So we have that under control. All right, so the magnesium has 2 electrons where the silver only has 1. So that means we need to multiply the top by 2 so we can get rid of our electrons. We have to balance electrons. If you're not balancing electrons, you're not doing your job. All right, so now what we have is 2 silver ions, 1 magnesium metal, and do include your charges. You must. Now, what I'm not making you do is write the state. In other words, the S, the AQ. If it has a charge, it is aqueous. The 2 silver atoms and the magnesium. Okay? So there's part A, right there. That's what part A is asking, the net ionic equation, okay? And we'll use information from that later on in the question. All right, part B says calculate the standard cell potential for the reaction written in part A. Again, these solutions are all 1 molar, which is very nice. So if they're 1 molar, we use the voltages that are on the standard reduction potential sheet. And again, going back to our standard reduction potential sheet, anything that's in standard conditions means that you're looking at a 1 molar solution. Don't forget that. That's a concept. All right, so figuring out the voltage, well, we have them right here. Now, what we can't do is solve for the math and then say draw an arrow and say, oh, there's our answer. Don't do that. Okay, it's okay if you want to write the numbers up there, but be sure to rewrite them. Okay, again, make sure that you're answering the question in the spot that it's asked. Okay, and you don't need a calculator for this. I hope not. Let me scoot that just a little. So positive 3.17 volts. Pretty good system. Okay, so there's your answer for part B. Part C says a cell is constructed based on the reaction in part A above. Draw and label all the parts of the galvanic cell when put together correctly. Place the anode on the left side. Also show the flow of electrons, anions, cations, and the current. Also indicate where oxidation and reduction are occurring. Okay. Now, not a bad question. I actually like this question. I hope it's on the AP exam. Don't worry about your artistic ability. Nobody cares how well you draw. Just don't be super sloppy and try to rush it. So what we need to do, and you have your chambers above, okay, and they want the anode on the left, so make sure that you respect them in that regard. Okay, and then I'll put my other chamber over here. Again, you don't have to be artistic about this. I'm not grading you on how nice of a drawer you are. Okay, so we have our anode on the left. So the anode's over here. Cathode's over here. Okay. Now, knowing who the anode and cathode are, don't forget, oxidation takes place at the anode. So our electrons are actually going to move in that direction. Okay, so our electrons are up here, and they move, in this diagram, they move clockwise. Okay. Also, we have to include our salt bridge. And we'll have our anions flow toward the anode. We'll have our cations flow toward the cathode. Pretty cool. Since electrons are going from left to right along the wire, current goes right to left. Okay. And again, current is the absence of the electron. So when an electron leaves that spot on the wire for a moment in time, there's a more positive charge there. Okay. The negative is gone, so it's more positive. So a current is not necessarily something that's physical. It's just the absence of those electrons, and they do move in the opposite direction. All right. Let's see. What else did they want us to... oxidation takes place here. And reduction takes place in this chamber. Now, again, actually, reduction takes place on the metal strip. Oxidation takes place on the metal strip. Now, what's not asked? Probably not a bad idea to identify it. This is silver metal. The solid is silver metal. In the solution, we have silver ions. Okay? So silver ions are actually accepting electrons, and we start to build mass as this reaction takes place. Okay? So we increase the mass at the cathode. And then this kind of breaks away. Actually, it looks like it's dissolving, but really what's happening is the magnesium is turning into magnesium ions, okay, which is pretty cool. Now, hopefully you're going to draw this a little bit neater than what I have on here. Again, I'm drawing it on my laptop, and I have my laptop screen at an angle here. But, yeah, take your time. You'll have a little more room to draw all this, and I think I did label everything. So, electrons, anions, cations, current, oxidation, reduction. Okay. All right, question number 2. Very, very similar to the first question. It says several different electrochemical cells can be constructed using the material shown below. Notice there's no salt bridge. We actually have a porous disk here. Question says, write the balanced net ionic equation. So again, that's the question. For the reaction that occurs in the cells that would have the greatest positive value for this cell. All right, so in this case, we all have one more solutions again. We have gold that has a +3 charge. We have aluminum, also +3, tin with a +2. And we also have aluminum metal, gold metal, and tin metal. And of course, our wire to connect the two. Don't need a salt bridge because our container actually has a porous disk, and so that's where the migration of the ions are going to take place. All right, so here's what I want you to do. I want you to figure out, go ahead and pause the video and try to design or answer the first question on your own. Seriously, pause the video, work this out on the example sheet, and then take a look at it. Okay? All right, so you've had a chance to work this out. We have 3 half reactions here. So we have gold plus 3. And again, I want to write out the reduction reactions first. You're looking at the standard reduction sheet. You're not actually writing these out. It has a voltage of positive 1.5. Aluminum. I honestly don't remember the aluminum right offhand. I know it's negative something. Aluminum. There you are. Negative 1.66. And then the 10 plus 2. And 10 right here, so negative 0.14. Alright, so hopefully you said that we're going to, this is going to be the thing that's reduced. The most positive we're going to keep as our reduction reaction. And then we're going to eliminate the middle of the road guy. We want to keep the most negative. Okay? So what we're going to do is we're going to oxidize the aluminum metal, and we're going to reduce the aluminum plus 3. Okay? So let me go ahead and clear those off. And then we'll answer the question here. So I think I remember the aluminum. Okay. All right. So gold plus 3, accepting 3 electrons. That's gold. And then we'll have the aluminum plus 3 electrons. And that had a negative 1.66. But now we're positive because we flipped the equation, and this had a positive 1.50. Again, we don't care about the total voltage on this. All we're looking for is the net ionic equation. So we'll cancel out the 3 electrons. We've got our gold plus 3, our aluminum, our gold metal, and our aluminum ions. So that right there is our balanced equation. Okay. Unfortunately, there are the same number of electrons on both sides, so there's no multiplier, so that kind of stinks. All right, B, calculate the standard cell potential. So again, we're going to take these 2 values here, and we're going to rewrite them and add them up. Okay, be sure to do that. Don't get lazy on this. These are easy points, and you definitely don't want to lose easy points. Okay, so there's your answer for that. Again, standard conditions mean that we're 1 molar. Okay, so all of these solutions are 1 molar. All right, part C says calculate the standard cell potential for the reaction when the concentrations are changed to either 0.75, 1.33, or 0.5. Now again, we're not going to use that because we're not using the 10. So again, the cell potential, this is under standard conditions, so we get to use the Nernst equation here, which is E cell is equal to the voltage under standard conditions minus 0. Come on, write it. 0.592 divided by N. N again is the total number of electrons, moles of electrons that are being exchanged. In other words, I have 3 moles of electrons here and 3 moles here. Okay. And again, back here we had 1 here and 2 here. That's why we multiplied everything by 2, because we need to have the same number of electrons exchanged. So for this problem, N is equal to 3, and we didn't have to do N last time, which was nice. And the log of Q. Okay. Now Q for this problem, again, we only include the aqueous solutions, or the aqueous ions here. We don't ever include solids in our Q. So we've got gold as our reactant, gold ions, I'm sorry, and aluminum ions. So again, don't forget Q is products over reactants. So we're going to have aluminum ions, and unfortunately it's to the first, and gold ions also to the first. Okay. So now that we have that information, now we can plug everything in and solve. And our voltage was 3.16 minus 0.592. Again, we said our total number of moles of electrons was 3. Log of, in this case, the aluminum is 1.33 to the first over the gold, which is 0.75 to the first. Okay, and also, don't forget this. This is a great concept. I have seen it asked numerous times. A question like this might be given to you on question 5 or 6 of the AP exam, and that's the part where you don't get to use a calculator. What they might do is they may give you a question like this. Instead of having you solve for the final voltage, they may ask you, will the voltage go up, be increased, or go down, or be decreased as a result of changing these concentrations? You have got to know what the values of log are when you look at a value that's greater than 1 or less than 1. Okay? Probably one of the easiest ways to remember, if you have a value of log that is greater than 1, like in this case here, 1.33 divided by 0.75, I guarantee you that's greater than 1. If I take the log of this value right here, it's going to give me a positive value. Since I have a positive value for this part of the equation, then that means my voltage will decrease. Okay, so my voltage should decrease. And actually, when I type all this information in, I get 3.155 volts. Okay, in other words, it was 3.16. Now it's gone down to 3.155. Now again, when we round everything off, we go back to our voltage. Now, getting back to our concept, if I had the 0.75 over the 1.33, in other words, our value is less than 1, if I take the log of that value, it will give me a negative number. And if I have a negative number and I multiply it times negative, that will cause the voltage to increase. So you have to know, as an AP chemistry student, that the log of some number that's greater than 1 will yield a positive sign or a positive value, which will cause the voltage to decrease. And if you have a value in your Q that's less than 1, taking the log of that value will now yield a negative sign, which will cause an increase in the voltage. Again, knowing the concepts is the most important thing for this AP exam. The AP exam consists of about 75% concepts. The only way you're going to get a 5 on this exam is if you understand and you study the concepts. Thinking that you're just going to get by doing the math, you're going to get yourself in a lot of trouble. Understand the concepts. Go through and reread the concepts. Okay? All right. Well, I hope this video's helped. If you have any questions, please don't hesitate. Send me an email.